We have consideration for selection of thermometric substance for thermometer. The first one is temperature range. The second one, sensitivity of the device and the environment. These are what you need to look into before you select your thermometric substance. Let's take for instance your temperature range. You must consider the temperature range if you want to select your thermometric substance. We have some thermometric substance that are good for some certain temperature range, and we have some other thermometric substance that might not fit for that temperature range. Let's take for instance, you want to measure temperature that is very low, below the freezing point. Now you will not select your mercury. Your mercury is not perfect for that kind of temperature because the freezing point of mercury is high. So you might not select your mercury. Your mercury cannot be useful there. Now another thing about temperature range is if you want to measure a very high temperature, you will not want to select a liquid that will easily vaporize. Let's take for instance, you want to select a thermometric substance. You are looking for thermometric liquid and you want to have that liquid inside your liquid in glass thermometer. Now you can't select, and you want to use your thermometer in an environment. You want to use it to measure a temperature that is so high. So you won't want your liquid to have what? Low boiling point. So that is that about temperature range. Another thing is the sensitivity of the device. So you might want to have a substance that is what? That is very sensitive in your device. You might need to consider the sensitivity of that thermometric substance. Now the last one is the environment. Now the environment is so important. And let's take for instance, you want to have a thermometer that you want to be using to measure the temperature of a furnace. Now you discover that the temperature is so high. So which means that if you want to select any material that you want to use as a thermometric substance, you must make sure that that material you are selecting must not be a material that will easily get destroyed. For instance, you want to have a thermometer, you can't just design any thermometer that you will have it inside your furnace. Is not possible because the temperature is so high, and at the end of the day that device can even melt. So that is why you can't use all this liquid in glass thermometer, all these thermometric substance liquid. You can't use it for that kind of environment. You need to use another device. That's why we use pyrometer to measure temperature of that kind of environment, because your pyrometer does not have to be in contact with the furnace. Now, how to increase the sensitivity of liquid in glass thermometer? The first one is the bulb size. You have bulb where you are going to put your liquid. Now, a smaller size bulb is used for quicker response to temperature changes, thereby increasing sensitivity. The bulb must be large enough to contain enough thermometric liquid, which means the bulb must be so small and it must not be too small so that you have enough thermometric liquid inside the bulb. The next one is a liquid with high coefficient of expansion is used to increase sensitivity. Now you don't just pick any liquid. Now don't forget that we want to how to increase the sensitivity. Now which means that you are using a liquid that has high expansion, high cubic expansivity. So which means that it can easily expand with small or minute change in temperature. That liquid will expand. So that is why we are going to select that kind of liquid. The next one is narrow bore. In narrow bore, we allow finer resolution in temperature measurement, thereby increasing its sensitivity. Let me explain this word, resolution. Resolution in measurement is how or to what extent can you measure can you measure something. That's what is known as resolution. Let me cite an example. We have some calculator that when you do your calculation, they can only give you 6 digits. We have some, they can give you measurement up to 8 digits. Let's say you can't compare this type. Let me give you an example of two measurements. Let's say I'm reading the temperature of an environment and I'm getting 70 degrees Celsius, and I use another device, I'm getting 70.1. I use another device that can give me my measurement, that will provide, even though the measurement is so small, is going to give me that value. And I have another thermometer that will give me 7.021. So the one that is giving me 7.021 is giving me high resolution. That is what we call resolution in measurement. You can also use your ruler to measure something, and when you measure that thing, let's take for instance, you have two ruler. One is just giving you 1 centimeter, 2 centimeter, 3 centimeter. That's what you can measure there. But you have another ruler that can give you 1 centimeter, 1.1, 1.2, 1.3, 1.4, and the like. That one can give you 0.1, 0.2, 0.3. So which means that the one that can give account of very small measurement, we call it has a what? High resolution. That's meaning of resolution. Now, high resolution, however, the bulb must be large to allow thermometric liquid to expand. The next one is capillary tube length. Now, the capillary tube length, increasing the length of the capillary tube can increase the sensitivity by amplifying the expansion and contraction of the thermometric liquid. This one is self-explanatory. Now, material selection, a material with low thermal conductivity for construction of the thermometer can help minimize heat loss and increase the sensitivity to temperature changes. Is very simple. Now, if you have substance that will absorb too much heat, we have another problem. Instead of expanding, it is absorbing it. So it means that that material, that substance cannot quickly expand. If you have any material, let's take for instance, we are still going to talk about it, but what I'm saying is, if you are talking about low thermal capacity conductivity, sorry, low thermal conductivity means that that material cannot absorb too much heat. So as you are supplying it, as you are using it to measure it, it is responding quickly, compared to if you have a substance that has high thermal capacity, it will just be absorbing the heat. So the next one is advantage of mercury over alcohol as a thermometric substance. If you are writing WAEC, you should know this, and you can even be asked in Jamb. Now, visibility, the first one is, we all know that alcohol is silver in color. Sorry, I said alcohol. Mercury is silver in color, visible in the glass tube of thermometer, making it easier to read compared to alcohol that is transparent. The next one is density. Mercury is denser than alcohol and it rise and fall quickly in thermometer, making it faster to measure temperature. Self-explanatory. Temperature range. Now the mercury has higher temperature range, freezing point minus 38.8 degrees Celsius and boiling point 356.73 degrees Celsius compared to alcohol. Now if you are talking about temperature range, just find a difference between the freezing point and the boiling point. For this guy, find the difference between freezing and boiling point. You see that the mercury has was higher temperature range compared to alcohol. It allows broad range of temperature measurement and also measure high temperature successfully compared to alcohol. Alcohol is freezing at this point. Mercury is freezing at this point. Oh yeah. Now the next one is thermal expansion and capacity. Now mercury has more uniform and predictable expansion rate. Don't forget that mercury is a melter. So that is why it has what? A predictable expansion rate. And this allows linear scale calibration of thermometer. Now if you are talking about linear scale calibration of thermometer, it means that as temperature is increasing, the expansion is also increasing. And if you plot the graph of the expansion, you get a straight line graph. So you get a linear scale calibration, and that is very important if you are having a measuring instrument. Now it also have high thermal capacity than alcohol, which means it release more, it can release and absorb heat more. It can easily release and absorb more heat for a given temperature changes. This contributes to the responsiveness and accuracy of the thermometer. Now, wetting of glass due to high cohesion in mercury molecules. Mercury has a concave meniscus and cannot wet glass. Now, let me explain this. Now, mercury has high cohesion. Now, the cohesion of mercury is so much that even if you have it in glass, the adhesion of the glass and the mercury is not, you can't compare it with the cohesion between mercury molecules. As such, mercury will not stick with the wall of the glass due to high cohesive force compared to adhesive force. That is why we have concave meniscus for mercury and it will not wet glass. Now, advantage of alcohol over mercury as a thermometric liquid. The first one is safety. Unlike mercury, alcohol is non-toxic. Don't forget that mercury is very poisonous. It's poisonous and alcohol is non-toxic. Another one is the expansion. Alcohol has a wider range of expansion coefficients than mercury and is suitable for specific range of temperature measurement. Now this guy, alcohol has a what? A wider range of expansion, which means that if you compare the coefficient of expansivity, cubic expansivity, down the one for alcohol is more than that of mercury. So that is why we give it thumbs up for expansion of alcohol. Now the next one is temperature range. Alcohol can measure lower temperature compared to mercury thermometer because alcohol has a freezing point. You can go and look at it. You see that the freezing point of alcohol is so low, so small, minus 114 degree compared to your mercury. That is around 30 something degree, minus 30 something degree. You see that at a temperature that is very low, you can use your alcohol as thermometric liquid. Upper and lower fixed point. Now, upper fixed point, this is the temperature of boiling water at standard pressure. Now, you need to understand the meaning of upper fixed point. Now, this one is at what? Standard pressure. Because if you are telling us the boiling point of water, boiling water can boil at any temperature. But at a standard temperature, at a fixed temperature known as this standard temperature, that is when we have our upper fixed point. The same thing with lower fixed point. This is the temperature of a melting ice. And don't forget, not just water, boiling pure water. If you have a pure water, the same thing. This is the temperature of a melting ice at standard pressure for lower fixed point, which means the temperature of ice, melting ice at standard pressure is known as what? Lower fixed point. Now we are comparing the upper fixed point and lower fixed point of different temperature scales. We have Celsius or centigrade scale here. We also have Kelvin scale here, and we have Fahrenheit scale here. Now compare it. We all know this 100 degrees Celsius for upper fixed point of water, and this one lower fixed point is 0 degree Celsius. Now for the Kelvin, we know this as well, 3730 Kelvin for the upper fixed point and 2730 for the lower fixed point. And Fahrenheit, you have 212 degree Fahrenheit for upper, and lower you have 32 degree Fahrenheit. This will save you a lot of stress if you know these guys. Try and master it because you might not even need to cram any formula. Just try and know that. That will save you from a lot of stress. And let's move to the next slide. Conversion of thermometer into different scale. Let's say we want to look at conversion, how you can convert from Celsius to Kelvin, Kelvin to Celsius, Celsius to Fahrenheit, and Fahrenheit to Celsius. You can also have it Kelvin to Celsius, Kelvin to Fahrenheit, and the likes. It's very simple. This is coming from the knowledge of mathematics. and this is also known as interpolation. Interpolation, we call it interpolation. Is very simple. You have your upper fixed point here, you have your lower fixed point here, you have a temperature measurement in Celsius. The same thing, just compare and contrast. Let's do the proportion, which means that for the fundamental interval, there's something we call fundamental interval. Difference between the upper and the lower fixed point here. Difference between the upper and the lower fixed point here, and the difference. Now, the fundamental interval between this guy for Celsius is 100. 100 minus 0, you have 100. 273 minus 373 minus 730, you have 100. 212 minus 32, you have 180 degree. You have 180 here, 100, 100. It's very simple. Now, which means that the difference between the upper and the lower over the difference between the temperature you want to measure, the value you are reading here, to the lower fixed point must be constant for all the scales. Well, let's do it. 100 minus 0 over C minus 0 must be what? 273 minus 273 over K minus 273. This is our K here. Is equals to what? 212 minus 32 over F minus 32 is F minus 32. Now, at the end of the day, you get this. Pair them one after the other. If you pair this guy and this guy, these two guys, if you pair them together and you try to solve the mathematics, you cross multiply, you get this. And if you solve it at the end of the day, you get, just try it, pause it, and pause this video and try this yourself. At the end of the day, you are going to get this. You are going to get K is equals to C plus 273. And don't forget, if you try to make your C sinusoid formula, you get this formula. C is equal to K minus 273. Which means you use this formula to convert Kelvin to Celsius. You just subtract 273 from it. Use this formula to convert Celsius to Kelvin. You just add 273 with whatever temperature you have in Celsius. Is so simple. We used to do this in chemistry most time. This is where it is coming from. Look at how we derive the formula. So let me just leave you guys to observe it very well. Now the next thing is, let's pick this guy and let's solve the mathematics. It's very simple. 100 over C will give you 180 over F minus 32. If you cross multiply, you get this guy. 180. Now divide this guy by 20 and divide this guy by 20 as well. 20, 20, you get 5 into bracket F minus 32 is equals to 9C, and you get 0, and you get this. At the end of the day, if you solve it and make your F, C solve the formula here, C solve the formula, you get this. Try and make your F solve the formula, you get this. Now let me quickly say something. This question used to come out, conversion of Celsius to Fahrenheit, Fahrenheit to Celsius. So try and cram this formula. If you don't want to cram this formula, there is a way you can solve it. It's very simple. That means you must know the fundamental interval, which is what, 180, and you try to do this simple mathematics. Just try to compare, do the proportion. That's all. You get your answer. Sorry, you get your answer. It's very simple. Upper fixed point, lower fixed point for Fahrenheit, whatever scale you are given, just fix it as well. Then you do the mathematics, you do the proportion. At the end of the day, you get your answer. So, and if you can cram it, just cram these two formula. Now the same thing that I just did, that's the same thing we've done here to get all these formula. Let's say, for instance, if you have your resistance thermometer, if you do the same thing, upper minus lower over the value you are getting minus lower is equals to what? 100 over C. Now if you solve it, at the end of the day, make your C solve the formula, you get this. Make your R solve the formula, you get this. The same thing with your pressure thermometer again. The pressure if you make your C solve the formula like this one, you get the pressure minus the pressure of the lower fixed point over pressure of the upper fixed point multiplied by 100. You get this. And the same thing with this. The same thing with the X thermometer means any thermometer that you don't know. And let's say they are telling you that a faulty thermometer is reading so at kinicon degrees Celsius at upper fixed point, kinicon another thing at lower fixed point. At the end of the day, you can use all this formula to solve it. You don't need to cram this formula.
The reading
Very
at upper
simple.
fixed point
And
and the
we're going
reading
to
at
see
lower
that
fixed
while
point at
solving
the
this
reading
job.
at a certain point, you can make the comparison. Just do the comparison, then you get your question. Yeah, let's forge ahead. Example 1. A platinum resistance thermometer record 3 ohms at 0 degrees Celsius and 8 ohms at 100 degrees Celsius. If it records 6 ohms in a certain environment, the temperature of the environment is... The question is so simple. You can pause this video and try to solve it yourself. Then you look at the solution. It's very simple. Let's get some insight from this question. Platinum resistance record these 3 ohms. It is at what? The lower fixed point. 8 ohms at what? Upper fixed point. Then we have a reading at a point which we don't know. That is what we need to do. The first step is to draw this, and let's use it to solve our question. Upper fixed point, the reading of the thermometer, the resistance thermometer is what? 8. Lower fixed point, the reading is what? 3. Now, at a temperature which we don't know, X, the reading is what? 6. Then do the comparison, do the proportion, which means 100 minus 0, 100, let me clean this guy, which means 100 minus 0 over X minus 0 should give you 8 minus 3 over 6 minus 3. Then let's go ahead and solve our question. Now 100 minus 0 is 100, X minus 0 is X, 8 minus 3 is 5, 6 minus 3 is 3. Then you solve your mathematics, find the value of X, cross multiply. 100 times 3 is equals to 5x. Then you have 5x is equals to what? 300. Divide both sides by 5. You get this. It's very straightforward and simple. As this question is simple, you will see some of them in your Jamb. Jamb loves bringing this kind of question. Now let's forge ahead. Example 2. Convert 90 degrees Celsius to Fahrenheit. Number 1. Number 2. Convert 130 degrees Fahrenheit to Kelvin. You can try it yourself. It's very simple. Now you are converting from what? Fahrenheit to what? From Celsius to Fahrenheit. You can use the formula that we've derived the earlier on. You can use it to solve these two questions. But I want you to pause the question and do it without using formula. It's very simple. Just go ahead and draw your two scale here. You have your Celsius scale here. Draw the upper fixed point of Celsius 100, lower fixed point 0, your Fahrenheit 212 and 32. Since you want to convert from what to degrees Celsius to Fahrenheit, so which means your reading here will be what? 90, and your Fahrenheit reading here is unknown. Just put F here. Oh yeah, do the mathematics. This guy minus this guy over this guy minus this guy should give you what? This guy minus this guy over this guy minus this guy. Then within 40 seconds, you will solve it without cramming any formula. The same thing goes with this one. Here, you have C here, and then you have what? 130 here. The same way you solve it. Now let's look at the solution, because I actually use formula to solve my question. You see, using the formula, very straightforward. Fahrenheit scale, to convert from what? Scale Celsius to Fahrenheit scale, you use this formula. Then you plug in your values. You get this. To convert from Fahrenheit to Celsius scale, you use this formula, you plug in the value, you get this. If you don't know how to cram this and this, you use the formal method. Let's forge ahead. Example 2. Example 3. A constant volume thermometer indicates a pressure of 215 millimercury at the ice point and 750 millimercury at the steam point. The temperature at which the thermometer indicates a pressure of 450 millimercury is. It's very simple as well. Pause it and solve it yourself. Let's look at the solution. Now, the solution is here. Very straightforward and simple. To solve it, you draw your diagram this way. Now, this question is actually solved using Kelvin scale. The upper fixed point of Kelvin, lower fixed point of Kelvin, the temperature at an unknown temperature, the temperature which you are finding, which is unknown, X. Then you draw another one again here, the upper fixed point of your pressure thermometer, the lower fixed point as well, pressure thermometer, and the reading at an unknown temperature. Then you do the mathematics. 373 minus 273, what you have here, over x minus 273, what you have here, should be the same thing with what? 750 minus 250, what you have here, over 450 minus 250, what you have here. Now, if you solve it, 373 minus 273, you have 100 over x minus this. This guy, if you solve it, you have what? 500 over 200, and you can divide both sides. You can cancel the zeros. Once we have two zeros here, just reduce the fraction. You get what? 5 over 2. Oh yeah, equate it. You cross multiply again. That will give you what? 5 into bracket x minus 273. I'm talking about this guy is equals to what? 2 times 100. That will give you what? 200. Go ahead and solve your question. Divide both sides by 5. If you divide both sides by 5, you are left with what? X minus 273 over 200 divided by 5. And 200 divided by 5 will give you what? 40. X minus 273 will give you 40. Go ahead and solve your question. X is equals to what? 40 plus 273. Then you get this guy here. So simple. You see that I'm actually using diagram. I'm not using formula. Now the next one, let's look at effect of heat. Effect of heat. The first one is expansion and contraction. Now, when I was explaining heat energy, which is also known as thermal energy, now heat can be in two forms. We can have positive heat and negative heat. Now, if you are having positive temperature gradient, that means the difference between the two temperatures is what? Is positive. Now you have what? What is known as positive heat. Positive heat is what we know as hotness, something that is very hot. Negative heat is what we know as cold. When something is cold, we are going to look at that later on. Then we have what? The first one, expansion. Second one, change of state, cracking. It can cause cracking. And thermionic emission of metals. Now, thermionic emission is what? When electrons are liberated from the surface of what? Hot metals. We have thermionic emission. We have change in chemical and physical properties of matters. We can all see that if you have a solid and you are heating it at a very high temperature, that solid will melt from what? From solid to what? To liquid. So that's melting, changing physical properties, and also as well chemical properties. If you have any compound and then you are heating it, it can what? It can decompose to form new compound. That's what we call chemical changes.